format for the whole week is that in the morning we're going to have sort of these high energy talks, high energy, high information talks. Then for the first 3 days, after the 2 talks in the morning, we'll have a tutorial. And then really the afternoons are, no talks, we really reserve them just for experimentation, interaction, trying things out. So there will be a lot of opportunity for socializing, interacting with one another. There are 6 organizers of this workshop. There also we've roped in some of our young friends and colleagues to serve. We have 6 teaching assistants. I propose that what we do now is we'll have Maria Inez will give us a tutorial on using Lean, and then we'll break for lunch. And then after lunch at 2:15, Pat Shapto. Pat Shapto is a DARPA director of a program focused on AI for mathematics. So at 2:15, he will tell us about that. And then at 2:30, I'll ask you to come back to this room, and we'll all introduce ourselves. We'll introduce ourselves to you. You'll introduce yourselves to each other. And then it'll be just a matter of opening up laptops and experimenting with Lean, and we'll help you do it. So that is the plan. And so without further ado, let me give the floor to Maria Inez, who's going to start showing us how to use it.
Okay, thanks. I wanted to close Git Lens, but I'm not sure how to do that right now. No. It's okay. It's fine, we can do it like this. Okay, so I'm going to give you the Lean tutorial. So Lean has already been mentioned today in the first talk by Floris. Lean is an interactive theorem prover. So it's a piece of software that we can use to write mathematical definitions, statements, and proofs using a very controlled language, and then the program will check for us whether the proofs that we have written are complete and correct. Okay. So the goal of this tutorial is not pretending to be a comprehensive vision of everything that Lean can offer. It's just get you to the point where you can read some basic Lean code and you can start writing proofs of basic theorems in Lean. Okay? So before getting into how to write proofs, I'm just going to show you some examples. And these examples are taken from elementary calculus. Okay? So for this, first I'm going to show you a couple of definitions that you might or might not remember, and then we will see an example of a proof using these definitions. So for this, the first definition will be the definition of limit of a sequence. So we say that a sequence U of real numbers converges to the limit L if for every positive epsilon there is some capital number n, such that for every n greater than or equal to this capital N, we have that the absolute value of un minus L is less than or equal to epsilon. Okay, so this is the mathematical definition. Now let's see how we write this condition in Lean, and so that we can compare how different it is from what we will write on the board, for example. Okay. So here when we declare a definition in Lean, we have to first give it a name. In this case, we are calling it sec limit, so limit of a sequence. Then we have to pass any parameters that this definition has. So the parameters could be objects, like in this case. So we have a sequence U of real numbers. So this is a function from the natural numbers to the reals. And then we also have a real number L, which is going to be the limit of the sequence. Something that is a bit different in Lean from regular mathematics is that in the board, if I were writing this on the board, to say that L is a real number, I will write it like this. L is in R, right? However, since we are using Lean, instead of this in symbol, we have to use a colon. Okay, so you can take this as a syntax detail for today, and just remember that whenever you see L colon R, this means L is a real number. Okay, and then once we have introduced our parameters, we put colon equal, and after the colon equal, we put what we want the definition to be. So in this case, the definition of being the limit of the sequence means that for all epsilon greater than 0, there is some n such that for all little n greater than or equal to capital N, the absolute value of this difference is less than or equal to epsilon. So a second small difference between what we wrote before and what we write in Lean is that to refer to the nth term of the sequence, we are just going to write U followed by n. Okay? There's no parentheses necessary. You can just write u and then the argument. Okay, and the second definition that we will use is the definition of a function being continuous at a point. So a function f is continuous at the point x0 if, again, for every positive epsilon, there is a positive delta such that for every real number x, if the absolute value of x minus x0 is bounded by delta, then the absolute value of f of x minus f of x0 is bounded by epsilon. We call this continuous at in line. So to say that f is continuous at x0, you will have to write continuous at f x0. And again, we have the name of the definition, we have the parameters that it takes, which in this case is the function from the reals to the reals, and then the real number x0. So it will be, the definition of continuous at f x0 will be that for every positive epsilon there is a positive delta. So far, same as we wrote before, such that for every x, if the absolute value of x minus x0 is at most delta, then the absolute value of the difference of f of x and f of x0 is at most epsilon. So again, here we are not using parentheses around the arguments of the function because they are not needed. You can just write f of x and f of x0. You do need the space. You don't need the parentheses, but you do need the space. Yeah. Okay. So now the example that I'm going to show you here is an example of a proof that uses these two definitions. And what this example says is that if the function f is continuous at x0, the sequence f composed with u converges to f applied to x0. Okay? So first, let's look at the statement of this result. So we are writing this as an example, so we need to use the example keyword. Then we have to put all of the assumptions that we have. So in this case, we have 3 of them that are objects. So we have the function f from the reals to the reals. We have the function u from the natural to the reals. We have the value x0, which is a real value. And then we also have 2 extra hypotheses, which are propositions, right? So we have the proposition that the sequence u converges to the value x0. And we have the proposition that the function f is continuous at x0. Okay? So we have to give some name to these hypotheses. In this case, we are calling them HU and HF, respectively. Okay, so once we have introduced all of the hypotheses, we put a colon, and after the colon, we put the result that we want to prove. So the result in this case is that the limit of the sequence f composed with u is the value f of x0. Okay. So once we have the hypothesis and the statement, we write colon equal by, and after the by, we will write the proof. Okay. You will also see this. Yes. Oh, yes, sorry, I meant to say that. Everything in green is a comment, okay, and everything that is not green is actually in code that is going to be executed or compiled. Okay. Yes. Okay. So after this colon equal by, we will have the beginning of the proof. We are also using braces here in this file and also in the exercises files that you will use this afternoon. So these braces mark the beginning and the end of the proof. They are not strictly necessary, but they are helpful, so we are going to be using them. Okay. Now, as Floris mentioned briefly before, Lean is an interactive theorem prover. And so far, we have not seen any of the interactivity. I've just been showing you some Lean code that I've written myself. To get to the interactive components, we have to use the info view. So to get that in VS Code, we click here, and we select the option toggle info view. And now we get a split screen. So on the left-hand side on the screen, we are going to be writing code. And then on the right-hand side, we are going to get the feedback that Lean is giving us from the code that we are writing. Okay? So now let's walk through this proof and try to understand how the right-hand side is giving us information. Okay? So again, at this point, I don't want you to try to understand all of the details, all of the instructions of the proof. I just want you to have a look at what kind of information you will get on the right-hand side. Okay? So the way this works is that you can put your cursor at any point in the proof. Okay, so any time after the by, any line inside the 2 braces that we are using, and on the right-hand side you will see the state of the proof at that point. Okay, So here we are just at the beginning of the proof, because everything in green is just a comment, right? So at the beginning of the proof, we have the function f, the sequence u, the real number x naught. We have that u converges to x naught, f is continuous at x naught. So all of these things that you see in red here are hypotheses. And then we have this special symbol, and after the special symbol, we can see the goal that we have to prove. Okay? So in this case, we have to prove that the sequence f composed with u converges to f of x. Now we are going to do a series of steps. So the steps are explained here in the comments. Again, I don't want you to focus too much on what they are, but it's basically the same proof that you will write on paper, but done in Lean. Okay? So the first thing that we do is, not strictly necessary, but helpful, is unfold the definition of set limit. So we are going to ask Lean to spell this out so that we can see exactly what we have to prove. So now we see that we have to prove something for all positive epsilon. So the way that you will do that usually on paper is, okay, so if I have to prove this for all positive epsilon, let's fix one positive epsilon, right? So that's what we do on the next line. So here, if I put the cursor after the next line, we see that the goal is different, right? We see that we have now introduced a real number epsilon with the hypothesis that epsilon is positive. So now we don't have the for all here anymore. We only have something that we have to prove for this particular value of epsilon. Now in the next couple of lines, we are going to use the hypothesis about, first the hypothesis about f being continuous at x naught. So we can use this hypothesis for this particular value of epsilon to get the corresponding value of delta, coming from the definition of continuity, right? So again, don't worry about the details, but this is done by this next step here. Sorry, yeah. Where?
So
yes.
where in the code does it specify that epsilon is positive? Like it says inverse epsilon.
Yeah, so I don't want to focus too much on the code right now. We'll get to that in detail later, but it's this intro epsilon h epsilon. So the first intro epsilon is introduced in the variable epsilon, and h epsilon is the hypothesis that epsilon is positive. So that's why we have it here. Yeah. But we'll see later in detail how these intros, how this works. So we'll see how to do this. Okay, so yeah, in the next step we use the continuity of f to get the appropriate delta that we have to use in the proof. In the next step, we will use that the limit of the sequence u is x naught. So we apply that to that value of delta that we just obtained, and that will give us the n that we have to use later. And then once we have that n, we end up with this goal to prove. So again, we have to prove something for every n that is greater than or equal to the n that we found using the hypothesis. So again, we are going to pick such an n, and in a couple more steps, we will be able to finish this proof. Okay? So I know that this was very fast. I was not pretending that you follow everything in detail. I was just trying to show how you are going to get information on the right-hand side as you step through the proof. Okay? Here, we can see that we have finished the proof because after this last step, these no goals appears. Okay? Like if I put the cursor before, I still have to prove something, but after here, we see that there is a no goals. Okay. So now what we are going to do for the rest of this tutorial is we are going to take a step back, and I'm going to tell you about how to write something like this. So how to do all of the instructions that we have seen in this proof, or things similar to this, so that you can start writing proofs similar to this one. Okay. All of the instructions that we have seen in this proof are called tactics in Lean. So a tactic is something that tells Lean, an instruction that tells Lean what it has to do in the next step. We are going to learn about several tactics today. Okay, so let me go here to this example. Okay, so in this example, you will see that many times we have the word sorry. Sorry, let me. I'm not using the right version of the file, I think. So let me go back. Now this will be the right version of the file. Yeah, so every time we see the word sorry on this file, we are going to change the word sorry by approve. So sorry is just a placeholder word that is telling Lynn, hey, I know that we haven't proven this yet, but now we are going to give you approve. Okay. So this can also tell you how the braces are useful. So if I remove the sorry, for example here, you see that there is a red underline here that appears in the second brace. Okay, so that means that there is an error. In this case, if you look at the info view, we see that the error is that there is some goal that hasn't been solved, but it could also be a different error. Okay, see, so this afternoon, when you are working on the exercises, if you see a red underline at some point, that means that there's something that you have to fix in the proof. Okay. But now we are going to learn about several different tactics that apply in different situations. So the first few tactics that we will see today have to do with basic computations. So the first one is called RIN, and this is a tactic that applies in the situations where to prove something you just have to use basic properties of addition and multiplication, like commutativity, associativity, distributivity, and so on. Okay. So here we have this example: a plus b squared is equal to a squared plus 2ab plus b squared. We know how to prove this, right? Like we just have to expand the left-hand side and then reorganize things in a different way and get the right-hand side. You could do that proof in Lean. You could do like all of the steps by hand. But the good news is you don't have to do it. Okay, so what you can do is you can go here and type ring, and then Lean will automatically apply these steps. So you don't have to do it all by hand. Okay? However, be aware that RIN doesn't apply any hypotheses that you have that are specific to your local context. It will only apply rules that are general about addition and multiplication. Okay, so things like commutativity, associativity, a times 0 is equal to 0, things like that. Okay. And then the second tactic that you can use is called congruent. So the congruent tactics states for, it means congruence, so it's short for congruence. And what this is going to do is going to try to prove equalities by comparing both sides of the equality, seeing if there are some things that appear on both sides. If they are, it will try to get rid of these things that appear on both sides, and it will try to check whether the remaining goal can be satisfied. Okay, so for example, here we now have f of a plus b squared is equal to f of a squared plus 2ab plus b squared. We know that this has to be true because by the previous example, we know that what's inside of the function application is equal on both sides, right? So the way that we can do this is we can first use the tactic congruent, and this will notice that we have tf on both sides, and it will remove it. But then we still have to prove the goal that the two things inside are the same, right? And we just saw that this is done by RIN. Yes. Yes. I will say later where everything is available. It's in the same repository that we will use for the exercises later. Yep. Yes. Yes, but here the hypothesis that we have in this example are that a and b are real numbers and f is a function from the reals to the reals. So Lean is using it. Also, something that I want to mention in this example is that before I told you that you didn't need parentheses for function applications, right? So we wrote f of x without the parentheses. But here, because you have a more complicated expression, you do need the parentheses, right? Because otherwise, Lean cannot figure out what goes first, essentially. So when you have a more complicated expression, like in this case, you have to write the parentheses. Sorry? Oh, sorry, this one, yeah, sorry. Okay, yep. Okay. Congress can be too eager sometimes, so it can try to unify too many things and give you something that is not true anymore. So if we look at this example again, we have two real numbers a and b, and we have a function f from the reals to the reals, and we want to prove that f of a plus b is the same as f of b plus a, which again is true because for real numbers a plus b is equal to b plus a, so therefore this will be true. However, if I try to do Congress like before, this gives me two goals that are not true, right? So this, the reason that this happens is because Congress will try to unify too many things sometimes. So here, it's first noticing that there is an f on both sides, so it's removing the f, but then it's also noticing that there is a plus on both sides. Okay, so it's trying to remove the plus as well, and that gives you two goals. The first goal will be prove that this a is equal to this b, and the second is prove that this b is equal to this a. So this is not good news. This is like something that went too far. The good news is that we can control it. So we can tell Lin how many steps we want Congress to take. So we do that by specifying the number right after Congress. So if we do Congress 1, it will only take the first step, which is to unify the f on both sides and get rid of it, right? And now we are in good shape because now we have a plus b is equal to b plus a. And since this is, again, a basic algebra equality, we can use ring to get the result. Okay. And unlike ring, Congress is able to use hypotheses that you have in your context. So here, in this example, we have three real numbers a, b, c. We have two hypotheses. No? We have the hypothesis that a plus b is equal to c, and then we have a function f from the reals to the reals. We want to prove f of a plus b is equal to f of c. So if we do Congress now, Congress does two things. So the first thing that it does is it gets rid of the f on both sides, and then it notices that we have an hypothesis that a plus b is equal to c, and it applies that hypothesis automatically. Okay. Now, sometimes in all of the examples that we have seen so far, we only needed to take one step or maybe two steps to finish the proof, but sometimes we might have to do longer chains of equalities or inequalities. And Lin provides one way of doing that, which is the calc tactic. So you can use this tactic to split a computation into several steps and then prove each of the steps individually. Okay. So in this example, again, we have three real numbers, a, b, c. We know a is equal to minus b, b plus c is equal to 0, and we want to prove that b times a minus c is equal to 0. So we will need at least two steps to apply this to hypothesis h and h prime. So in this example, the way that we are going through the proof is first we have b times a minus c is the same as b times minus b minus c. So this is done using Congress because Congress can realize that we have h telling us a is equal to minus b. Then in the next step, we can reorganize things a little bit. So we can pull this minus outside of the parentheses, right? This is, again, something about basic algebra, so it gets done by ring. And then in the next step, we will want to use the second hypothesis, b plus c is equal to 0. So we do Congress again. Now b times minus 0 is equal to 0. Again, it's basic algebra, so we do ring. So whenever you want to do a computation with several steps like this, you can use calc to achieve this. You have to be a bit careful with the syntax of calc. Let's do it step by step here. You want to make sure that all of the underscores are aligned well. So like all of these underscores that appear here should be at the same level. Like if I try to move one of these here, then this will give me an error. Okay. The good news is that if you are just starting and you are not very familiar with the syntax of calc yet, Lin can help you. So you can do calc question mark, and this will give you the first step, let's say, in the computation. So what this does is it just creates a calc block with your end goal. So in this case, the end goal is c is equal to 0, so this is what it creates. And now you can, again, get help from Lin to write down the next steps that you want in the proof. Okay. So let's look at what hypothesis we have in this example. We have 4 real numbers, a, b, c, d. We know that c is equal to b times a minus d, d is equal to a times d, and we want to conclude that c is equal to c. So there are, of course, many different ways that we could go about this, but perhaps the more obvious is we first try to apply that c is equal to b times a minus d, right? So again, if you know how calc works, you could just write the next steps yourself, but you can also get help by Lin. So the way to do this is you put your cursor after the colon equal by, and then you go to the info view, so you go to the right-hand side, and you select the part that you want to replace. So in this case, we want to replace this number c. So we can do shift click, and you will see that here we get this option to create a new step. So if I click here, now this is going to introduce the next step on the left-hand side, and it doesn't know what I want to put on the left, right? So I have to write what I want, which in this case is going to be b times a minus d. Okay. Now I'm going to do this again on the next step. So here, now I want to use the second hypothesis that tells me what d is. So again, I go here, I shift click over d, create a new step, and now I want to replace this by a times d. Okay? Yes, so now we see that we have 3 stories because there are 3 different steps that we have to prove, but we can do this with the tactics that we have already learned about. Okay? So the first tactic is going to be conquer, because this is just applying an hypothesis that we have. Again, the second tactic is only applying an hypothesis, so we use conquer again. And then for the last step, now this is algebra again, b times a minus a times 3 is equal to 0. So this is going to get done by ring. Okay. There's a last example here using calc. And here I want you to notice 2 things. So one thing is that in calc, you can work with equalities, but also with inequalities. Okay? So in this case, our goal is to prove an inequality. A plus b is less than or equal to 3 times b. So we can do this by combining first an inequality and then an equality, for example. This is perfectly valid. Right? And the second thing that I want you to notice in this example is that conquer doesn't work for inequalities. It only works for equalities. But we have another tactic that is able to handle inequalities, and that is called G-conquer, for generalized congruence. Okay? So for this first step here, G-conquer is applying the first hypothesis, A is less than or equal to 2 times B. Okay? Okay. Now there is one last tactic for doing computations that we are going to use today, and this is just called simp. So the simp tactic is simp for simplifier. The way this works is it's going to look through the mathlib library. In the mathlib library, there are many lemmas that are marked with a simp attribute. And this simp tactic will try to apply all of these lemmas to the current situation. So any lemma that possibly applies to the situation until it finds a proof. So for this example, we want to prove that the absolute value of x minus x is equal to 0. So in Lin, in the mathematical library, we already have a lemma that tells us x minus x is equal to 0, and we have another lemma that tells us that the absolute value of 0 is equal to 0. If you know how these lemmas are called, you can apply them directly, but again, the good news is you don't need to know how these lemmas are called. Right? The mathlib library is very big, and it's impossible to know how everything is called. But sometimes we can use some automation tactics like simp and some other tactics that we'll see later to find, so that Lin can find which lemmas it has to apply without us having to remember all of the names of these lemmas. Yes?
So is simp stronger than conquer and ring?
It's different. Simp, yeah, I mean, ring, for example, only works with things that apply for commutative rings. So any object with a summation, with an addition and a multiplication operator, satisfying the hypothesis of commutativity, associativity, so on. That's the only thing that ring is going to try to do. the simplifier is going to try to apply lemmas that are marked as simp in the library. So again, not every lemma in the library is marked by simp, but some of them are. So simp is going to try to use those lemmas that possibly apply to your proof. So yes, they apply in different contexts. Okay. Now, let's see how to work with different logic operators. So the first one that I want to consider is the universal quantifier for all. Okay? So let's look at some examples. We have to learn about how to use a for all when we have a for all in an hypothesis. And we also have to learn about how to prove a statement of the form for all x, something is true for x. Okay? So to do this, let's look at this example about, again, functions from the reals to the reals. We say that a function is an even function if for every x, so for every real number x, f of minus x is equal to f of x. So again, notice that I don't need the parentheses on the right because x is only one word, right? But here on the left, because of the minus, I do need the parentheses. Also note that I didn't need to tell Lynn that x is a real number. Lynn is able to figure out by itself, okay? Because Lynn notices that f is a function to the reals, and I am applying f to x here. So it will be able to deduce that x has to be a real number for this to make sense. If you are in more complicated situations, sometimes you will have to tell Lynn what you are trying to apply to, but here Lynn can figure it out. Okay. Now, one way that we can use these examples where we have a for all in an hypothesis is by using the apply tactic. So in this example, remember the definition of even function is that for all x, f of minus x is equal to f of x. And here we have a goal that is to prove that f of minus 3 is equal to f of 3. We do this with the apply tactic. So the tactic apply is going to see that we have a for all x something is true, and it's going to specialize that for all x to the value that we are passing. So in this case, we are passing the value 3. So it's specializing this for all statement to the value of 3, and therefore it can conclude the goal. Again, some good news here is that Lynn is able to do a bit more for us. We don't actually have to provide the value 3. Lynn is able to figure out that that is the value that it has to use. Okay, so in here we have exactly the same example, but instead of writing apply HF3, I'm just writing apply HF. And Lynn is able to see by itself that because I have a 3 here in the goal, this is the value that it has to try to apply it to. Okay. Now, we have seen how to use an hypothesis of the form for all x p of x. Now let's see how to prove it. So if we want to prove that something is true for every x, like for example here we want to prove that the cosine function is even, so this means for every x in the real numbers, cosine of minus x is equal to cosine of x. So since we want to prove something for every x, we start by fixing one x. So I'm going to call it x naught here, but you can give it any name that you want. Okay, so if I call it x naught, you will see that here on the goal I am applying this to this particular x naught. But for example, I can also call it a, say, and then the goal becomes cos of minus a is equal to cos of a. So this is a variable, you can give it any name that you want. Okay, and then we can hope that this is already proven in the mathematical library of Lynn, and indeed it is. So we can use the simplifier, and the simplifier will find the proof of that. Okay. So yeah, we do intro to specialize to one particular value of x, and then we have to find a proof that the statement is true for that particular value of x. Okay. So now let's look at a slightly longer example where we are going to apply hypothesis of the form for all x p of x, and we are going to prove a goal of this form. Okay, so now we have the hypothesis that f and g are two functions from the reals to the reals. Both of them are supposed to be even functions, We want to prove that the sum of these functions is also an even function. Okay. I will also take this opportunity to introduce the tactic unfold. And the tactic unfold is used to tell Lin that we want to spell out some definition. Okay, so in this case, we can do unfold even fun to spell the definition of even function. And since we have it appearing 3 times here on the info view, we can use it at each of these steps, right? So in the first line of the proof, we are doing unfold even fun at HF, right? So this will change the first hypothesis, and it will change it to just writing out the definition. So for all x, f of minus x is equal to f of x. And then we do exactly the same thing as at the second hypothesis hg and at the goal. Okay. Notice that these steps, these unfolding steps, are not necessary for Lin. So Lin already knows that this is the definition, but they can be very helpful for us because maybe we don't remember what the definition is, and this way we can see it precisely. Okay. So now we want to prove a for all statement. So always the way to prove a for all statement is you start by fixing one element. So we do intro x naught to fix a real number, and then we do a computation to check that f plus g applied to minus x naught is the same as f plus g applied to x naught. So we can use again calc to split this computation into several steps. In the first step we write f plus g applied to minus x naught is the same as f of minus x naught plus g of minus x naught. There's a lemma in the library that tells us that this is always true. Like when you apply a sum of 2 functions to an element, this is the same as applying summing the applications of each of the functions to this element. So we use simp because we don't care about what the name of the lemma is. We just want to use it. And then we have to use the 2 hypotheses that we have. So first we have to use the hypothesis that f is even, and then we have to use the hypothesis that g is even. And this is what is done in the next 2 steps. Now we are going to see 2 options for how to write this proof. The first option is the one that is written here. So here we are concatenating 2 tactics. So to do that, you need to apply this semicolon here so that this compiles, right? So the first application, this congruent one, in this case is going to notice that g of minus x naught appears on both sides of the equality, so it's going to get rid of it, right? So now here the goal is now to prove f of minus x naught is equal to f of x naught. And now, since this is a particular case of the hypothesis HF, we can apply HF to finish the proof. Okay? So we do that. And then in the next step, we will have to do the same for G. So we do congruent. So in this case, the congruent one will get rid of the f of x naught that appears on both sides. And then we apply HG for this special value of x naught to conclude the equality. And to put it back into this form, we use simp again. Okay. So this is one way to do it. In this way, we have to do like two small steps in parts 2 and 3 of this calc computation. There is another way to write this proof a little bit differently, which is using this specialized tactic. So what this tactic does is whenever you have a goal of the form, not a goal, you have an hypothesis of the form for all x p of x, and you only care about applying this goal for one particular element, you can use the specialized tactic to replace the for all statement to the application of the statement to that value. Okay, so here again we start by fixing any real number x naught, and instead of working as before, instead of going directly to the calc computation like before, we are going to first specialize HF and HG for this particular value of x naught. So after specializing f to x naught, now we get a more concrete hypothesis. We get the hypothesis that f of minus x naught is equal to f of x naught. And then we do the same for g. So we specialize h of g to x naught. And we now do the same calc block that we did before. The difference is that in the second and third steps, before we had to do congreg 1 and then apply the hypothesis. But because we have already specialized the hypothesis here, now congreg is just able to finish. Okay, it was not able to finish before because it didn't know that you had you were able to specialize the hypothesis to this particular value of x naught. But because we have already specialized it here, at this point, Lin is able to use these goals already using the tactic congreg. Okay. The next logical operation that we are going to look into is the implication. So for this example, let's look at a new definition of non-decreasing function. So a non-decreasing function is a function from the reals to the reals, such that for every pair of real numbers, x1, x2, such that x1 is less than or equal to x2, we also have that f of x1 is less than or equal to f of x2. Okay, and we can also use the tactics intro and apply when we have implications instead of the universal quantifier. Okay, so I also want you to notice that the symbol that we are using for the implication is not the double arrow like you will usually do in the board. It's the same symbol that we use for functions to the reals, for example. Okay, so in this implication P and Q, the symbol that I'm using is exactly the same symbol as I'm using in this function from R to R. And a reason for this is that Lin interprets the implication P implies Q as a function that takes as an argument a proof of the proposition P and returns a proof of the proposition Q. Okay? Which is also the reason why you can use these tactics intro and apply when you have implications. Okay, so let's see how to use it here. So let me maybe do this step by step. We have a function f which is non-decreasing, and we have two real values, x1, x2, with x1 less than or equal to x2. We want to prove that the same is true for f of x1 and f of x2. So we can unfold the definition of non-decreasing to remember what this means at hf. And if we do this, now see that the goal that we have, f of x1 is less than or equal to f of x2, is the last part of this hypothesis, right? So because everything that we have before this line is either a for all or an implication, we can use the tactic apply to work for us here. So there are different ways that we can go about this. The first is we can do this in several steps, asking Lin to work a little bit for us. So we can try to apply HF and see how far Lin can go from this. So Lin is able to go pretty far. So Lin can see that because our goal is f of x1 less than or equal to f of x2, it can figure out that we want to apply HF for these particular values, x1 and x2. Okay. So after the apply, however, we still have to prove something. We still have to prove the left-hand side of the implication. Right? We have to prove x1 is less than or equal to x2. And now this is an hypothesis, so we can do congreg, for example, and this will be able to finish. So you can do it like this. You could also just pass all of the arguments explicitly. So you could also tell Lin that we want to apply HF, specialize the values x1, x2, and hx, which is the hypothesis. Okay? So you have two options here. You can be very explicit about all of the arguments that you want to apply, or you can let Lin do some of the work for you, and then just finish the proofs of every side goals that appear. Yes?
Can you give an example when you do something wrong and it complains?
Yes, sure. So, for example, let's see. So here,
you did everything correctly, so you say, yay!
Yeah. Okay. So here, for example, if I try to do this, so apply HF instead of applying it to x1 and x2, which will be the correct thing, I can ask Lin to apply it to x1 and x1, right? And then Lin is going to complain because, okay, so it's going to say, if you want to apply this hypothesis HF to x1 and x1, the next thing that you have to give me is a proof that x1 is less than or equal to x1, but instead you are giving me a proof of x1 is less than or equal to x2, so it will complain. Okay, so, yeah, and you can, depending on what you do wrong, I guess, you will get a different error message. And unfortunately, some error messages are more informative than others, but in this case, it was pretty informative. Yeah. Yeah, so. Okay. Okay. There's another thing that I want to say about how to find lemmas in the library. So we have already seen one way of using lemmas from the Mathlib library without knowing what they are called, which is using the simplifier. But you can also use an apply question mark tactic. So in this example, well, I've already done it here, so let's do it right now. So we want to prove that if we have a continuous function f with compact support, then there is some number x such that for all y, f of x is less than or equal to f of y. So this is proven in the Mathlib library, but I don't know what this lemma is called, right? So what I can do is, if I guess that something is proved in the Mathlib library and that just one step or maybe several steps can get you the proof, I can try to do apply question mark, and this will give you suggestions of how to proceed. Okay. So in this case, this works in one step. So this gives you something that completely closes the goal. You can click on the right-hand side to replace the apply question mark by the proof that Lin was able to find in the library. Yeah, and this apply, again, is not going to do magic for you. What this is going to do is it's going to search to the library and try to find lemmas in which the conclusion of the lemma is the same thing as you have in your goal, or something that specializes to your goal, maybe, and it will give you options for how to proceed. In this case, it finds something that works in just one step, so it gives you that. In more complicated situations, it could give you several options, and maybe none of the options close the goal completely, but they could make progress in the proof. Okay. Oops. You can, yeah, but let's not do that today. Yeah, biostat could be collapsed, but yeah, let's do everything in tactic mode today. Yeah. Okay. Okay, so we've seen how to work with uniformal quantifiers. Now let's do existential quantifiers. So there exists some x such that some property p is true for x. Again, we want to know how to use this in the hypothesis and how to prove them. Let's start with how to prove them, because this is a bit easier in this case. So here, the example is that there is some natural number n such that 8 is equal to 2 times n. We know that this number is 4, so we tell Lin use the number 4. Now, in more complicated situations, there will still be something to do after this, right? Like, after you provide the value, you will have to prove that the value that you have provided actually has the right property. But in this case, the property that you will have to prove is that just that 8 is equal to 2 times 4, right? And in Lin, this is true by definition. So this is the reason why in this case we don't need to do anything else. We can just do use 4. Okay.
So if there's more than one variable in the context, you have to use u then colon 4?
Well, no, because in the goal, there's only n, right? Like, if you have like several existentials combined, you will do use for each of them in order, right? So like if you have exist x1 n2, you do use, say, use 4 for the n1 and then use 5 to the n2 or something like that. see how to use hypothesis of the form there exists some x with p of x. Of course, in that case, what we want to do often is to, okay, if we know that there exists some x such that this is true, can we get an element, can we get a witness for this property, right? And the way to do this in Lean is using the R cases tactic. So the R cases tactic, the way it works is you first pass it the hypothesis that you want to use, then you do with, and then you tell it how you want to split it. So we'll go back to this in a minute. Let me first say what the goal is in this example. So in this example, we have 3 integers a, b, c. We have hypothesis that a divides b and b divides c, and we want to conclude that a divides c. So couple of things to notice here. So first thing to notice is that this divisibility symbol is not just the bar on your keyboard, right? This is a Unicode symbol, so you can type this using a / bar. And also I should mention that more generally, where you are seeing that in Lean code you are using all kinds of Unicode symbols, right? Like we are using symbols for the integers, for example, for the real numbers, for existential and universal quantifiers, and so on. If you don't know how to type these symbols, you can always put your mouse over the symbol and it will tell you how to type it, right? So like, for example, here for the divisibility, it tells you that this is /bar or /divide, like there may be different options. Or for example, in the existential, we can type this with /ex, so on. In particular, for these symbols in the R cases, these are weird brackets. So to get these brackets, you have to do / less than or / greater than. Okay. So yeah, let's in particular see how we are applying this this example. So the hypothesis H1 is a divides b. So a divides b by definition means that there exists some other integer k such that b is equal to a times k. Okay, so this is the existential that we are using. So we apply R cases to H1, and that will give us the value of k and the property that k satisfies. Okay, so after this step, we see that in the info view we get the integer k and the proof hk that b is equal to a times k. Now we apply R cases again for the second property. So the second property is going to tell us that there exists some L with C is equal to B times L. So R cases is used to produce such an L. Now we want to prove that there exists some other integer such that A times that integer is equal to C. Now because of what we found in the first 2 steps, we know that that integer is going to be K times L. Okay, so we tell Lean to use K times L. And now we are not so lucky as we were in the first example where everything was true by definition. Here there is a little bit of work that we have to do. Okay, so after the use K times L, we have to prove that the value that we have provided as a witness is a value that actually satisfies the property. Okay, so in this case we want to prove that K is equal to A times K times L, and we can do this using again a calc computation where we are going to use Conger a couple of times to apply hypothesis and then bring to finish the computation using algebraic properties. Is what?
Not that clear. That A divided by C, not C divided by D.
So this tells you that C is divisible by A.
C is divisible by A.
Yeah, so A divides C. Yeah. Yeah. But again, if you hover over the symbol, the divisibility symbol, you can see how it is defined. So, yeah. So this gives you the definition. A divides B means that there is some C such that B is equal to A times C.
Yeah, it was taken from what definition in my head that A divides.
Yeah. But yeah, you can hover and see how it is defined. Yeah. Okay. Yeah, so the last logical operator that we want to discuss is the conjunction. So given 2 statements P and Q, the conjunction P and Q says that is the statement that says that P and Q are true. both of them. Okay, so we want to learn again about how to use it in a goal or in an hypothesis, right? So here, let's do both things at the same time. Our goal is to prove Q and P, okay? And whenever you have a goal of the form something and something, the first thing that you can do is you can try the constructor tactic. And what this tactic is going to do is it's going to split the goal into two new goals. So one goal will be to prove the left-hand side of the conjunction, and the other goal will be to prove the right-hand side. So in this case, the first goal is going to be proving Q, and the second goal is going to be proving P. Now, we also have as an hypothesis P and Q. So this will tell us how we can use a conjunction that appears in an hypothesis. And we can do this by using the name of the hypothesis .1 or .2 to access the left or the right sides. Okay? So in this case, our hypothesis is called H. We want to use the second part because we want to prove Q. So we do apply H.2. So that closed the first goal that we had, but we still have a second goal, right? So we are going to do now apply H.1 to get the other part. Okay, so let's stop now, or do I have? Okay, yeah. So now we have seen all of the ingredients that you need, but yeah, let's go for lunch and then we can continue. Yeah.
So again, if that looks also it's a lot of information, full of scary. Don't worry, that's what we're here for. Break for lunch. Come back at 2:15 here past Shafto. Then 2:30 we'll finish up the tutorial and then the game started.
Can you go to the top of the file so we can see the import statements?
Yes, sure. I don't know if these are very helpful because this is something that we are importing from this project. Again, like later we will be to the repository that we are using, so you will be able to see everything. Yeah.